There are another way, they call it electric resistant corrosion probe. These probes, they inserted in a similar situation like the other one, and it end up with a little wire like that, like wire. You can have it carbon steel, stainless steel, whatever material you like. They're available, all kinds of metals. And this wire, when you insert it in the surface, it starts corroding. So the cross section of the wire becomes smaller. So electric resistance becomes higher. So you can, from this change in electric resistance, you can correlate that to corrosion rate. And the electric resistance of this wire or this probe, they call it electric resistance probe. There is an corrosometer portable, goes and hooks up to this end of the wires and measure the resistance of wire. And then each time you make a measurement, you plot it in a curve, and from that curve you can there is a formula, you can calculate your corrosion rate. And if it is high, then you see why and take care of it, make it changes in the process. This one is called electric resistant probe. There's another one, they call it linear polarization probe. It is similar, it has two electrodes like that. It has a certain voltage. If corrosion happens, this voltage changes. And from that, it is correlated to corrosion rate, and it has also it can be measured here. And even these probes, they are used, even they can go to the control room and give you a reading, and can affect ammonia injection. It can be used to control a lot of things automatically. It's like part of the control system. Electric linear, but this is only applicable when you have water stream electrolyte system. It doesn't work when you have hydrocarbon liquid or something, because it doesn't, not electrically, not quite electrolyte. Okay. These are the tools that are used to install and remove the Cobans or the corrosion probe on a stream without shutting down. They hook up to the fittings that is on the pipe, and then once it's hooked up, you hook up to and then remove the Cobans, and then close this valve, and you're back in the stream. You take it out, weigh it, etc. And then if you'd like to replace it, you put a new one, and then hook it up here, open the valve, takes the pressure, and then insert it inside, and then close your valve. Remove the retriever, they call it corrosion retriever kit. They can, some of them, they can go up to as 3,000 pounds of pressure. They can handle them, but you need very good experienced person to do that. It's very risky if you don't know what you're doing. So these are the techniques of corrosion monitoring, and I hope it is good enough for now. The other activity of our group, it is welding and manufacturing. It is we call it, it's different from corrosion, and but it is very important in our part, because we buy equipment, buy piping, and these equipment piping are all welded, assembled by welding. And if it is not properly welded, you end up also with catastrophes, problems, cracking due to bad welding. So these are types of welds that used in fabrication, like fillet welds here, like butt welds here, different butt welds, double butt weld, welded from inside and outside. Some of them are V, some of them, like they call it, different V. Some of them would have backing strip, but that is not here shown. Some of them angle. So there's different types of welded joint, but this is an example how the equipment are assembled, nozzles and shell courses and heads of vessels, how it is welded together. There are different processes for welding, and which we usually see in fabrication of these equipment and piping systems. And the first one is the simplest one, is the shielded metal arc welding process, and in abbreviation it is SMAW. It has an electrode. Of course, the electrode is connected to a source of energy, electric current, and the other end of the circuit is connected to the pipe. This electrode, it is a metal inside, matching the base metal you're welding. If it is stainless steel here, the electrode is stainless steel. Once it touches the metal, it creates a spark, arc, and the arc creates a lot of heat, so it melts the wire itself inside electrode, they call it here, and it melts the base metal, and so you have a pool of weld metal here, and then you move. Once you move, this solidifies. This molten metal, if you don't protect it, it will get oxidized. So instead of having molten metal, you will have oxides. So you should have shield to avoid air from getting into the molten metal. And this shield has come from this covering, this flux, they call it flux. It also melts and provide shielding around gas around the molten metals to avoid getting air in here to oxidize this molten metal. So otherwise you end up with corrosion products or oxides instead of metal. So this is one of the, you end up with weld metal covered with slag from the flux covering the metal, and then later on you remove the slag, you knock it off, and you end up with the metal, weld metal. So this is the one, they call it the stick welding, for commonly used stick electrode welding. They call this one stick. The second technique of welding, they call it sub-arc welding, SAW. It is it is mainly used in fabrication shops, mass production. It is a high speed. It requires a lot of current, and it is very fast, produce a lot of welding. But it is used in automatic machines. What it happens that you have an electrode continuously fed to this pool of, to this groove of to be welded, and it is covered by flux to protect it from oxidation, to protect this metal from oxidation, and it pours in molten metal and molten base metal here, and is covered by the flux. And this way it is very get a good weld, and it is very fast and very productive technique, but it is automatic machine applied, and it is always used in producing mostly vessels, heat exchangers, sometimes big nozzles, but is a big piping if it is done in the shop, but it is not applicable for field application. You don't use it in field. The second technique, this gas tungsten arc welding, they call it GTAW. It is this technique. It is very slow. Is intended to have clean weld metal, and it is usually used for the first pass to make sure that the first pass is a good metal and good quality. And the principle of it, you have tungsten electrode in the metal which generate the spark and the arc. And once the heat is developed, you feed your filler metal, your welding metal that will melt and fill this thing on the side. The welder has in his hand and put it in the arc so it melts with the metal, base metal, and foam, and make the weld metal. Again, the protection gas is by argon gas. Fed his argon gas goes around the electrode and cover this whole spot to avoid oxygen getting into the molten metal and oxidizing it. So this technique, they call it TIG welding or GTAW welding. It is used low speed, low production, but it's very good quality, and we like to use it for the root pass of welds. The initial pass, when I say root pass, the initial pass. There's another technique, they call it gas metal arc welding. In this case, the electrode is the wire itself. The electrode, instead of having tungsten electrode, you have the wire itself is the electrode, and it is fed continuous. It is like you have a reel here of wire, which is intended, And this one is much faster than the TIG welding, and that's why they like to use it. And gas goes around it. Also, in this case, they don't use argon or helium or carbon dioxide or mixture of those gases. It forms this protection layer, and that's the way of doing it. It has two different types. They call it short arc, which is very weak arc and low heat input. That's why we don't like it for thick wall welds, only for the root pass. But there's another way, they call it a short arc, means the arc here goes very short and it doesn't, very low heat input. But there is another way, they call it spray applied or pulse, which has more energy and more heat, and you can use it for heavier welds. This one, they call it MIG welding, coming from metal arc welding. This is the last one I have here. We can allow, they call it flux core arc welding, FCAW, but with gas shielding. And this one, it is the electrode itself goes inside the gun, but inside the electrode, the flux is inside the electrode, and the gas again outside. So you have here double protection: the flux plus the gas, and it is very fast. Fabricators, they like it because it is very fast. Saves them a lot of time, means a lot of money. And this way, many people didn't like this process because it is dependent, labor dependent. Quality of it is labor dependent. But people, they start learning it, and the filler methods has improved lately very much. So people are using it now more and more because it is productive, saves money for the fabricator as well for the purchaser. So this is another type. There is another one which is it has no flux, no gas shielding. The gas is generated by a flux, but this is a non-reliable process. That's why I didn't put it here. In fabrication, so we go out and buy equipment, buy piping. So the fabricator, per the requirement of purchase order, they require to submit welding procedure qualifications, welding procedure and qualification record of it. And the purpose of that we would like to make sure that these fabricators, they have procedure that can produce welds as good as the base metal. You don't want to have something that you weld and you end up lowering your quality of your product. So the procedure, they develop a procedure for each one for any of those processes I mentioned before, and they decide what thickness range it should be, and do you need heat treatment, no heat treatment, etc. Decide all, set it up, and then they make a test, take a test piece, and let a welder do it, and then test this test piece and see the quality, mechanical properties of test piece. If it passes certain criteria established by the code, this procedure becomes acceptable for this. So these procedures need to be reviewed by us and approved, and we make sure that this procedure is applicable to the equipment we are buying as far as heat treatment, the thickness range, is it meet the code requirements, does it qualify properly, and once we approve it, the fabricator is allowed to start fabrication. They also submit weld maps, which I didn't put here. Weld maps, which, like, for example, you have a vessel, you have this weld, that weld, this vessel weld will be prepared, made by this procedure, and we make sure that each weld is made with qualified procedure that we have approved already. The qualification of procedures is done according to the code to which this equipment is built, and Section 9 is commonly used for pressure vessels and piping. We use API 1104 pipelines and piping designed to this thing, or API codes. and we use the AWS standard for structural steel welding qualification. So we do a lot of course, in welding, I didn't cover, during fabrication, fabricators have a lot of problems in fabrication, cracking, they didn't use the proper material. They come to us and ask us what to do. There's a lot of NCRs, deviations we have to deal with fabricators and the equipment engineer to resolve them. Non-destructive testing, although we don't do the non-destructive testing ourselves, we specify them for certain applications. Non-destructive testing itself, even not done by our quality group, is done by the local quality people in the fabrication shops. Our quality people are qualified to do this non-destructive testing, but as our group, we are familiar with it, and we recommend use some of them if it is needed for specific quality requirements. And these techniques are radiography, which is used, it is like you make your teeth to check the welds quality, and code tells you this is acceptable, not acceptable. For example, cracks in welds are not acceptable. You have to cut it and re-weld it. If you have porosity, there's some limits for porosity. And if you have undercut, this is acceptable, not so this radiography is used for ensure that the welding quality is good. Of course, radiography can be used also to measure voltage. If you make a panoramic, I don't know how, X-ray for a pipe on the side, they give you the thickness of the pipe and can check the thickness of the pipe. Magnetic particle testing, it detects cracks on the surface, a little bit under the surface. There are different ways. They use a magnetic field, and then on the equipment, so generate a magnetic field on the surface of the weld or the equipment, and then you spray powder like iron powder. And if there is a crack, so it makes discontinuity to the surface, you can see a line which is a crack, so you can say there is a defect. And there is dry powder or wet powder or wet fluorescent magnetic part which has fluorescent in it, which like sparks and you can see easier, is more sensitive. Another technique, they call it liquid penetrant testing. This is you spray, if you have a crack on the surface, these penetrants, they have ability to diffuse or goes into very tiny cracks. And then the penetrant is always like red color. Then you clean it up, and then the penetrant is still in the crack. Then you spray a developer, like white liquid, which dries very quickly, like powder-like, and it absorbs the penetrant from the crack, and you can see a red spot on the powder. And this is a useful technique to find surface cracks. Eddy current is another technique which generates some eddy, and is useful for the examination of heat exchanger tubes that are welded, and make sure there is in production, mass production, there is no cracking in the tubes. Visual inspection, of course, is very important, which is like 90% of the inspection. The code have all these things are listed there and give guidelines how to do them. Leak testing, tank bottoms, you can use leak testing. There's vacuum boxes, they call them. It generates some vacuum, and if you have and you put some soap suds on the weld, and then you create vacuum. If there's a leak from the bottom, it makes bubbles, so you know there is a weld is leaking, is not perfect enough to repair it. There is leak testing of systems. Acoustic emission, you generate some vibration, and you measure it, and any discontinuity in the metal can be detected as a noise. And so these are all governed by the code. There's a limits and how to do them in the code, these 7. And then we do also ferrite testing in the weld metal and the weld overlay. The reason for this ferrite testing, if you have high ferrite content, this can form like sigma phase under heat treatment conditions. And you have sigma phase means you have brittle weld, it means cracking later on. If you have a low ferrite content below 4%, means when you weld this, when you have possibility of cracking in the weld while welding. So we always, the optimum limit for ride testing is many people specified like between 4 and 10. We have to be within that range. As I mentioned before, positive material identification, make sure that you use the proper materials. We specify there are instruments to use that, and we have our specification for it. And the clients, they have their own specification as well. It tells you how to do it, what kind of instrument to use, what elements to check for in each type of material. So these are techniques used for non-destructive testing. We don't do it ourselves, but we specify them if it is necessary to avoid corrosion problems. Okay. We prepare a lot of, usually we use client specifications. We don't really, this is one of the areas we have to improve. We have our own specifications, but we have the tools to do them, but we don't have the time. But we use client specification if it is required. We develop the specifications needed for the project. These specifications are a list of what we normally do or deal with: welding and fabrication of pressure vessels and piping. Welding, we have to tell them what is acceptable, what is not acceptable to use, what is the limits, what testing you have to do, what acceptable welding materials to use. All these limitations, it is in addition to what the code tells you. It is a good practice. And there is an API document also for welding. They call it API 582. They give you also some guidelines, but we have to use our judgment to specify what is needed. We specify material requirements for wet sour service. Carbon steel, if you buy regular carbon steel, probably it will crack right away. But there is special steels, special chemistry, special production, how they make them, how to inspect them, how to heat treat them, equipment, how to produce them. We have to specify to avoid wet sour corrosion problems. For chrome moly steels, as I mentioned before, they are subject to temper embrittlement, and there are standards to specify them. And also, in addition, there is a client requirements. And we can specify what is needed in the chemistry, what is needed on testing, what is needed on how to produce the steel, how to weld this equipment, and what kind of inspection you need after fabrication. We put also material requirements for materials that will be used in the creep range. Some of actually in the CCR units, which operate above creep range, if you don't specify the proper metallurgy, you end up with also creep and cracking due to high temperature operation. We prepare positive material identification. Actually, we have one for that. Reinhard prepared his group prepare insulation specification for hot service, insulation for cold service, insulation for acoustic purposes. We prepare specification for fireproofing, or review and use fireproofing. We prepare specification for galvanizing. Very important for steel structure where they use galvanized steel. Sulfur plants, we use a lot of refractory and heaters. They have the specification for materials and how to apply them. Painting and coating, what kind of painting to use for each type of service. Temperature, is it inside, is it immersed inside an equipment, is it immersed, is it a lot of requirements, and you have to specify the proper painting, and this all spelled out in the specification. If you need to chemically clean a system for cleanness, for example, oxygen service, or due to corrosion problem, we can develop procedures or a specification for chemical cleaning. Chemical cleaning can cause a corrosion problem, can cause damage if you don't do it properly, if you don't control it properly, so we have to prepare a specification for that. It includes all the controls on that. Cathodic protection, we can prepare a specification how to design a system, how to apply it, and during construction. I think almost this is a lot. This is a curve we came from API 510 for allowable stresses, how to select allowable stresses for heater tubes. And the simplest way is if you are designing for 500, if your skin metal temperature is 500, and you are designing for 100,000 hours, then your stress, maximum level stress is 4,000 pound, 4 MPa. Otherwise, the life of the pipe will be less than 100,000. So you have to select your wall thickness to generate at least maximum 4 megapascals. And there are some other curves. This is a tensile, this is a yield, and I don't remember what these are for. This, I think, Larson mirror, which is used to estimate heat treatment requirements. I think I'm done with my part. If you have any questions, we can take, I don't know, I'm ahead of schedule. Have